All right. Good day. Good day, everyone. Good day from wherever you are. My name is Nemeka. I'm a data scientist at Amway AI Labs. I'm going to be continuing from, I think this week, I think was that Tuesday on, I'm going to continue on the classification task, the Titanic data sets class, sorry, solution. And so let me share my screen. All right, I hope my screen is visible. Okay. So today, quick recap. We're trying to predict the survival of a passenger on the Titanic. Um, so we got the data set from Kaggle and we are we are done with the feature data analysis, right? So we read in the data, we did some data analysis on it. We found out the missing values, we found out like their statistics, how they are spread out, and we thought about how to like resolve it. This is most likely the boring part of the work, but it's kind of the most crucial part of everything, right? So we did some analysis, did some plots, and we found the important features that would be needed, right, for this particular to help this model, right? So it's about predicting survival, right? So yeah, we looked at the different features and how they are distributed, right? And their react interactions with other ones, like other features like the embark, their sex and their fare that was paid, right? And yeah, we dropped those unimportant features. We we now did feature engineering, right? We created a new feature called title, and we moved the name, the name table, I mean name column, right? Um, Found out that okay, this feature is interesting, it's quite helpful. So we left it in and we dropped the name. We dropped the passenger ID because it's just a number that is serial, right? We converted the categorical features to numerical because normally your machine learning models don't understand categorical features, right? They understand numerical features. The question on the chance. Okay, you said you can't hear me. Can you hear me? Can you guys hear me?
Yes.
Okay, someone said you couldn't hear me, so I hope you
Yes,
can
we
hear me.
can hear you.
All right, whoever that is, most likely your speaker, or your earpiece. Right. So yeah, we continue the analysis and let me just continue. Then we did something called um binning, right? We binned the 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 age feature, right? The numerical feature, because we found that it was skewed, right? There were some values that were just quite higher than the rest, and they skewed the whole distribution of the values, right? So we kind of binned it and put it in like in some bins, right? If you know how a histogram is, a histogram bins some particular values depending on how you set it, right? So we did something like that, right? And we put it into 5 bins and we chose we chose how we wanted the bin should be, right? If you're less than 16, you be in a bin. If you're greater than 16 but less than 32, so that's how we binned it and we dropped the age feature, right? So the thing is that the whole machine learning, the whole data science workflow it's iterative, right? You might actually do this binning and find that it didn't help your model, right? Then you go back and you just use the age feature just like that. Okay. we just use the age feature just like that, and you find out that the model is better. So it's all iterative, right? There's no like one fit or one size fits all for the data science workflow, right? Okay, so we created the new feature family size, right? That is the combination of the sibling and the patch, and we created an is alone feature, right? It's the person traveling alone, it's the passenger traveling alone. Then we dropped some of those features because we found out that they might not be very, very helpful, right? We created a new feature called age class, right? So it's kind of like an interaction between the age, right? We created like the age and the class, right? So it's kind of interaction of each age in each classes, right? In each class of the of Titanic, right? So depending on the age in that class, they are more likely to survive because they are more likely to be let go, or they're more likely to be like to give because the issue with what happened with Titanic was something about there were not enough lifeboats, right, on the ship. So they most likely use something like an age or and also the classism, right, to choose who will be on a lifeboat and who will not be on a lifeboat, right? So that's just how it worked then, right? So yeah, that's why we created the feature interaction age and class. And we dropped, okay, yeah, we found out like um because the embarked feature was not complete and it has some missing values. So what we did is that when you want to fill missing value, it depends on is it categorical or is it numerical. If it's numerical, you can most likely use different kinds of imputing methods. You can use the median, you can use the mode, you can even create your own imputing method. That's what we did here, right? And if it's categorical, just like string values, right? You most likely use the mode, right? The most occurring category and you impute that because it's most likely possible that that particular person just didn't was not just filled, so you just put in the most occurring category, right? And so we did all of that. I need to be fast, right? And so we got to this stage where we binned the fares and we dropped the numerical part of it, like that's the numbers, right? And now we are where we want to do the prediction. So now we're going to the machine learning part of it, and I imported a library train test kit. I know you guys know about this. So and we created the X and Y train sets, right? And we now want to do the train test kit. So we split let me choose 20% in this case, right? So right, right. So the test set will be 20% of the whole X value, right? And the train set will most likely be 80%, right? And we choose a random state and I want to run it interactively. Right, so for today, we'll most likely just do logistic regression. You can always try out the nearest neighbors, SVMs, or just go to decision trees and random first and see how it works. Today, I'll just most likely be explaining what all this F1 score confusion matrix is all about, right? And how they help you decide, or how do you decide which one to use? Right. So okay, so we imported the logistic regression class and fit on the train and we predicted on the test. Now this is the train accuracy. Let me print this out. Right. Let me print this out. This is the train accuracy. Right. For wasting your time. Okay, so we're putting out the train accuracy as 80.9, right? And we can also get the test accuracy, and we print that out. Is the test accuracy. So we can know whether the model will fit or not, right? And I'm sure by now we all know what overfitting is, and we kind of know in our head how to curb overfitting. Okay, so um, So yeah, we see that yeah, we multiply by 100, anyone, right? They all work. We see that okay, it most likely overfits, right? But this is just like this is for the this is for logistic regression, and there might be a reason for this, right? It might not just be it's overfitting. So there's something they call the confusion matrix, right? And I want to say that the reason why the reason why you use something like confusion matrix and not just accuracy. You use that in when you have an imbalanced class or imbalanced classes, right? So how do you know what is imbalance, right? So let me do something for you. Let me show you the value count of the so what I'm doing is I'm counting the values in my y, right? That's my target variable, right? Y is the target variable. And I want to show what is the count, what's the ratio of survivor and non-survivor, right? So if we show that, we see that in this particular data set, um, there's more of the people that didn't survive than the people that survived, right? And it makes sense because they said it was 38% of people that that were 32, sorry, 32% of that were in Titanic that survived, right? So now, but this is an issue, right? Because if you base your machine learning, your metric on just accuracy, right? This is a very, very simple example. But in an example where you have like 90% of the false case and 10% of the true case, like something like cancer, images of cancer cells, right? Or images of breast cancer or whatever cancerous, any of these rare diseases, right? You most likely have people that don't have it, right? More than people that have it, right? So let's say you have images, right? And in the images, you have 95% of them are what do you call it? Are not positive, they are negative for cancer, and 5% are positive of cancer, right? So if you give it to a machine learning model, and the machine learning model just predicts everything as negative, right? It means that the accuracy is 95%. I don't know if you can picture what I'm saying, right? So I don't know how I'll depict this in mathematics, but um, right. I don't know how to type it out. I just want you guys to get a picture of what I'm saying, right? Um, so let me repeat that again. So imagine you have in your data set, right? You have 95% of people do not have cancer, they're negative, and 5% of them have cancer, right? And you just build a model, and the model just predicts negative all true, right? And that is negative, like just 000 all true, right? The thing is that the accuracy of that model will be 95%, right? To be 95% accurate because he predicted 95 of it negative and there were actually 95 with are negative, right? But in the general sense, what is very, very important to you is the people that are not that are cancerous, right? Predicting those people that are cancerous very well, right? And that's when you use other metrics other than accuracy, right? Because accuracy will be kind of biased, right? So that's when you have things like the confusion matrix. And the confusion matrix is just like a matrix of numbers, right? Matrix of numbers that might not make sense initially. Wow, why is okay, yeah, I use 20%. So it doesn't make sense just from looking at it, right? But if I do some kind of use Seaborn heat map, right? So heat maps you work better with matrices, right? So you put in a matrix, you format the output into digits, right? Then you set your X label, you set your Y label, right? You set your X ticks, right, and your Y ticks, right? And you put your title, it becomes clearer, right? You can see things clearer with images and graph, right? So we see that on the y-axis is the actual, and on the x-axis are the predicted labels, and we know that um this is the true positive, right? And this is the true negative. No, sorry. anyone, right? You can say this is a positive and this is a negative, depending on whatever use case you want, right? Um, so we can see that these are the ones that odd one out, right? And we see that it's it really had some very high false, is a false negative, right? And false positive, right? And this is when you want to um choose what case do you want to use, like which particular sorry which particular metric are you going to use? Because we have already decided that accuracy will be not useful here, right? It will be biased, right? So we can now say we can choose between precision and recall. And I'm sure from your material, you know what precision and recall, the formulas for it, right? I just got this from the sklearn, scikit-learn documentation. This and you see that if we look at the precision, if you print that out. So it said that a value close to one is best and a value close to zero is worst, right? And so that means that if you want to optimize for precision, right? You want to get your model to be optimized for precision. What does that mean exactly? So I got an example, right? So in precision, you want to reduce the false positive, right? You want to reduce the um, let me give you a use case, like I said, email spam detection, and you have a model that will determine spam and not spam, maybe a particular email is spam or not spam. So in that use case, you want to optimize for precision. Why? Because you don't want because a positive will be it's spam, right? A positive case in this will be that the particular email is spam. And so if it's a false positive, that means it's a very, very important email that was classified as spam. And that email will go into the user's spam box or the spam inbox and most likely not the same because not many people check their spam. And but that's a very, very important email, right? And so in this kind of use case, you want to optimize for precision. So you want the precision to be as high as possible, right? And you don't care about false negatives, right? So that means there might still be some spam emails that or some wrong emails or bad emails that or bad mails that are classified as not spam, right? There are some spam emails so you don't really care about that, right? So but you care that a user's important email doesn't go to spam because you will not want that, you will not like that, right? So that's when you want to use something like precision, right? And now we can go to something like recall, right? So what's the recall? Recall is most um focused on the false negatives, right? And so what does that mean? Also, there's a use case, right? So let's say, like I said, the cancer, the COVID-19, and most of them are most likely used in medical field, right? So this metric is most likely used in medical field, and what it means is that you don't want a false negative. So let's say during the COVID-19 pandemic, and you have a model that determines if the user is COVID-19 positive or is negative of COVID-19. So you don't want a false negative in the sense that someone that is actually positive, right, and is not classified as negative. And if that person goes out there, you have a higher spread of people of COVID-19, right? So that's how COVID-19 was like fast as well, right? Because it can transmitted through cough and through the air and through contact and a lot of things. So yeah, so if you had a model in that time and you wanted to use a what do you call it, a metric, you must like use the recall, right? So you can reduce the false negative and you don't really care if somebody that is negative is give is is predicted as positive, right? Because yeah, the person will be quarantined and the person will be quarantined and there's not really side effect. You can get your vaccination and you're you are free. Like let me just split it out there, you're free, right? And so yeah, so that's when you use something like a recall, right? So yeah, so if we check out the recall, also that's the value zero is what you want, right? And zero is very, very bad, right? And so we can see that we have pretty high precisions and recalls, but not really that high, right? We can do better than this. And also have something called the F1 score, which is like a combination of the both of them, right? And um I really don't like, yeah, you can always like say like, okay, you have in your own use case, right? You want a high precision and you want a high recall, right? And you want like a combination of them. So the F1 score, like most of all of these, you can just check the your sklearn the scikit-learn documentation, right? And let me see if I can search metrics, right? In metrics, if I go back, sorry, so where will it be? Metrics to F1 score, precision, F1 score, yeah. So you can see like a different ways in which they calculate it, right? The default is binary, right? And there are different other ways you want to um calculate. There's a micro, there's a macro, there's a weighted. I personally don't know how all of these work, right? Right. So whenever you like ever need to use it, right? Because I personally have not used F1 score that deep, right? And so if you want to, you always find the documentation and you always find like people that or blogs out there that explain what all of this mean, right? So depending on your use case, because in most times in machine learning, you are the one that define your metrics, right? The metric is not given to you. You just are told, you're just told by the business or the C or the users that this is what you want. And so you determine the metrics depending on the use case, and you are the one as the data scientist to choose which one to use, right? So yeah, you check out documentation, you check out blogs and read up on that metric. And yeah, there's a Wikipedia entry for it too if you want to go down that deep into using Wikipedia to find out what this is, right? So yeah, this is the F1 score, right? And no, sorry, this, that was a primitive function. So if I print out all of this, and the thing is that if you want to know now you have trained in logistic regression model, right? You can always like choose, okay, this is logistic regression. You choose a metric you're optimizing for and try it out on another machine learning model. So let's say I want to use a random forest, then just come here and copy this ones. I'll just check it out by my right. And so I want to see if a random forest model will perform better than this, right? So I just come in here and I define the random forest model. Have I imported all of that? Yes, I think I have. So um I would like to use the default any number of estimators, right? So I just leave that as it and I change this um X test. Y train is not defined. Okay, still using it. So and Y train, sorry. I'll most likely just print out the train accuracy or strength. And I'll print out all of this for the decision tree. Okay, so oh, we see that the train accuracy quite was quite higher, or it's higher than the that of the logistic regression, and we want to get out the precision, the recall, and all of that for it. So let me just copy in all of this so I don't repeat code. Remember, this is just repeater notebook. In real world, sorry, you most likely are going to define a function, right, already, and you just need to call that function. But since we're just doing some experimentation, yeah, you can just use something like this, and that will work. Uh, right, so let me call this widespread random forest, right, instead. random forest. And okay. So if I do that, I copy it into here and I print out this. Let's see what it gives me. All right. So we see that it actually performed better than the logistic regression model by some distance, right? So um, the thing about experimentation is that at first you just want to, but we see that it's overfit a lot, right? We see it's 7 and 0 points. So okay, let me calculate the accuracy and see how it overfits, how much it overfits. Okay. The accuracy. Okay, so we see that it's overfit by almost 6. And if we compare it with the accuracy of the logistic regression, okay, 78, right? So it actually did better than it, right? And so now that we know that, okay, this particular model is the best, right? Then you can now move on to other things like hyperparameter tuning. Hyperparameter tuning as in um you hyperparameter tuning as in you choose you start selecting what hyperparameters you need to change so that you can affect like the model. So I wish I can load the different hyperparameters here, right? So you see NM estimators, the criterion, the max depth, the mean samples leave. And so you know that in this case, because of how great this is, you know that this model is overfitting. Then you have to look for a hyperparameter that does regularization, right? So yeah, that's when your data science powers come in, right? So you now look at like what are the hyperparameters you can change or tune so that this particular distance will not be this high, or you go back to your feature set and choose and think around. So if you can make this particular accuracy better than normal, better than how it is now, or you can choose another model you can always use XGBoost. XGBoost is most likely the trending model for classification and regression nowadays. XGBoost, LGBM, light gradient boosting, and yeah. So I would like to also point out something, right? That a since we know that this is a imbalanced classification task, right? Imbalanced as in, like I said, the you most likely want it to be 0.5, 0.5, or 0.4, 0.5, right? Or sorry, 0.4, 0.6, right? Or 0.45, 0.55, right? You don't want it to be this long, right? Because if it's long, you're most likely seeing you're now seeing an imbalanced classification task, right? So also there's something in train test splits called the stratify, right? And let me see, it's going to load that. The stratify. So what this does is that it looks at your y variable, and when it is splitting, when it is doing the split, it splits it with the same distribution as this, right? So how would I put it now? Where is it? So we found out that this is the distribution, right? So when you use the stratify also in this X test and X train, the distribution is also maintained. So how can I explain this, right? So let me show you what Y train is, right? Y train dot value counts, right? Value counts, normalize, true. We see that the distribution here is most likely different. It's most likely okay. It's not that different though. Still close. or not that different. 0.61612. Okay, 0.62. So let's see also for the white test. Have I run that code before now? All right, so we see that it doesn't really follow distribution because you always want your test set and your train set to like follow a certain distribution. Here you see in this case, there are more survivals in the test set than actually in the train set, right? And in most cases, you want because in real life, the distribution of your train set should replicate your test set should replicate that of your train set, right? Like for example, like in that cancer cell, the use case I was talking about, your train set is most likely 90 to 10% or 95 to 5%. So your test set should also be 95 and 5%, right? So you can, it's more like there's a particular term that is called, but it's more like distribution is more in the same range, right? So that's when they stratify why um variable comes in place. So if you now check it out and see what's the distribution, we see that now y test is following that distribution. And let me use this for y train. Y train. Let's see how it is. Yeah, so we see now that they follow the same distribution. And if we train the model now with this, we hope for I'm not going to be certain that it's going to be improved, but we hope for an improvement. And we see that in the train and in the test, was there an improvement? Maybe a slight improvement or not? I can't remember. But we always hope for an improvement in most of all these situations, right? So let me look at the confusion matrix and F1 score again and see. See that there was a change here, right? There was a change in the values. And if we print out the precision, okay, the precision reduced, right? And the recall also reduced. So most times, most of all these are just standard. It's how will I put it? It's like a standard in data science that you want your train and your test set to be more to replicate themselves, right? Because so it would give you like a true representation of what your accuracy is, right? So if there was more there was more of it in the test set, it's not going to give you like the true metric, like the true metric, like the true accuracy or the true precision, right? So right now we see that even though it changed, it kind of tells us like how are we actually performing with this model, right? And so we now like use that to grade, right? The next iteration of models are going to use because like I said also, like I say, you always want your train and your test distribution to follow. You want your train and your test like features to follow too. You don't want something called data leakage, right? You don't want your model to be cheating and stuff like that, right? So that's when you always like to follow, you want to follow these set rules in your data science workflow. Right. So I think I've covered most of the material in for today's class. And if you want the notebook, it will be shared with you from the channel. And are there any questions that you would like me to answer? You can always ask me now. Okay, so I see one in the chat. Okay, so I want to add also that in an imbalanced classification problem, right? There are other methods that you want to raise to make it more balanced, right? There's something called smooth. Smooth is like um is a technique that helps you like generate synthetic samples from already existing samples, right? So you can push up the the balance to be more equal, like to be more even, right? So you have smooth, and there are most likely other techniques that you can use to curb that in data of over 9,000 columns and still use it for modeling. All right. Um, in my personally, I hope I'm still audible. 9,000 columns is a lot of columns, right? In my time as a data scientist, um, used not just pandas, right? There are other tools you can use, like let's say Spark, right? Spark is most likely overkill, right? Spark is most likely overkill, and um, they have also there's the package called Cool, I think pandas on GPU, right? So in this case, you're not using pandas on your CPU, you're using pandas on your like on your GPU, and you know that it's more efficient and it's faster than using pandas on your CPU. Also, there's also like something called sampling, right? You sample some columns out of the whole list of columns and you use that for your modeling, right? You don't use all the columns, right? Most of these columns have names, right? They have um it's already a schema, like from your data engineer, there's a schema you have, right? And you know most of these columns, what they are and what they are used for. And then you now select out of them the ones that you feel will be most necessary. And that should most likely streamline the number of columns that you want to use, right? But also in some cases, like in medical, I work in a medical data set, and they don't want you to throw away any data, any column, right? Because you feel like they feel like those columns are important, right? Like let me say in DNA, something DNA related, right? So that's when I was able to use something like pandas on GPU, right? Yeah, but the other use case you can use Spark, right? Spark for data exploration, and that's when you see something like cloud computing, exploration on the cloud, right? Where you can use something like AWS, I think Athena, I don't know, there are some, let me say the popular one, Google BigQuery, right? BigQuery like a data warehouse where you can do a lot of data exploration. Then in that table query, you can do modeling, machine learning modeling from there, right? So in all those large cases, in those large use cases, you most likely have to use the cloud when you can't fit all of that in your memory, or you can use GPUs depending on if you have a GPU. So yeah, that's solution. That's my own take. You can always set your line for another solution if it's not suiting for you, right? So I hope that answers the question, Daniel. Paul, you said I did not get last class notes. What last class note? Do you mean the notebook? Yeah, if it's the notebook, it's still the same notebook I'm using, right? I just built on top of the previous notebook, right? And all of it is here for you to use and try out something, right? So that will be the end of today's class. And I would like you guys, I would like every one of you to try it out. You can't learn by just reading, right? You have to learn by actually coding, right? By actually typing some code. So yeah, try it out in your spare time and yeah, you will surely get better. Thank you.
All right. Thank you, sir.
Hello, can I ask a question? you can ask, but I think our speaker maybe network issue or something.
I'm available.
Okay, so
Oh, okay.
I think about a month or two ago, I was working on a personal project on data sets to predict it's a medical data set to predict heart disease. So from where I got the data sets, they already had professional machine learning scientists and data scientists who had already worked on it, and they gave a particular uh, range of precision, accuracy that they got when they did it. So when I did mine, I was able to get that I was able to get my accuracy, precision, and rest to fall in that range. I've tried everything to improve it. I used hyperparameter tuning. Um, I also tried to use feature importance. That is, sorry, not feature importance. I tried to use the correlation of um, different features, how they correlate with the target variable. Uh, I dropped some of the columns that the what's it called? The correlation was very, very, very low. Then what's other thing? Yeah, clean the data and every other necessary thing I needed to do. I used the pipeline. I used pipeline to the sklearn pipeline to um,
Yeah.
scale the data as well. But there was no real improvement to that level. I think the minimum was about 72, 73%, but I was getting around 60 something thereabout. And I've tried everything possible. I don't know if there's any tip I could get to, work on it
Like you
to
said,
improve the.
you said it's medical, right? It's medical data. It's medical data set,
Yeah.
right? So I feel, sometimes in most machine learning tasks, people figure out that this particular data they give you is not helpful. It's not helping you get a good accuracy. I've seen it sometimes some cases where people go out and fetch other data sets, right? Not as if other data sets, some features that will be helpful, right, for the prediction of this particular, helping in predicting this particular case, right? So
Yeah.
most of the times it relies on domain knowledge, more feature engineering, right? Feature interactions, right? And the truth is that most of the times, especially in medical use cases, right, to get those very, very high accuracies, except it has been attained. In your own case, has it been attained or you have been trying to attain it?
No,
Has it been attained?
they said they've attained it, like from the
Okay,
website. There was a
all right,
range. Yeah.
all right. So it's most likely in feature engineering, like actually looking at those features and because there's something called post modeling like analysis, like after you've done your modeling, you go back and look at your carefully look at your particular data, right? Look at
Yeah.
are those places where it did not predict right? Then you do some analysis. What is happening here? Like why in that particular place where it's predicting wrong? What's wrong? Right? That's why I think it's called post-modeling analysis. Not many people go that far, right? Like you said, they were machine learning scientists specifically that worked on it, right? So they
Yeah,
had a
machine
lot of time,
learning
and
data
yeah,
scientist.
so yeah, and that's you. You're just one working on it, right? So don't beat yourself too much, right? It's just left for you to um keep on doing some analysis, post-model analysis. When you model, you're not really done. That's where the careful analysis on where those wrong predictions are happening. Why is it happening like that, right? And those machine scientists might have used some advanced techniques that you don't really know about. So I'll
Okay.
maybe advise you to check out some books, right? To grow yourself, you have
Yeah.
to read some books, and especially in data science. So you maybe just check out some books, read on some books, papers. Maybe I'm not sure about the papers, but some books like maybe feature engineering, feature selection. There's this book, feature engineering, feature selection book, right? It really explains, but
Okay.
it's very, very technical, right? A lot of technical jargons in it, right? So that almost likely
Sorry,
what it is.
do you have a link to it, to that particular
I don't
book?
have a link to it, right? I don't really have a link to it. But I don't really have a link to it, but I've seen the book out there and it has a lot of technical jargon, right? So yeah, you most likely just need to read, do some domain exploration on that particular task, right? So yeah,
Okay, thank you very much. I really appreciate it.
no, well, all right, yeah, you're welcome. Take care.
All right, thanks.